Now we have to talk about taking derivatives of tensors on manifolds. In flat space-time, in Cartesian coordinates and Lorentz frames, we use the partial derivative. And we talked about how the partial derivative, acting on some tensor of any rank, actually defines another tensor for you, in the sense that if you computed the coordinate components mu, alpha, beta in one coordinate system, and you did the same operation using another coordinate system, these two formulas are related by the tensor transformation law. That was in flat space-time when the tensor transformation law only meant Lorentz transformations. Now that we want to use the tensor transformation law for any coordinate transformations, this is no longer true. And so we need to revisit our notion of a derivative. And what we're going to do to fix it up is we're going to introduce a covariant derivative, denoted by the upside-down triangle symbol. And that is going to have the property that you could do it in two different coordinate systems, and the result you get would be related by the tensor transformation law. And by the end of the video, we'll have a formula for this covariant derivative. Now, one thing you could do to make a derivative like this is just declare that I'm picking a fiducial coordinate system, where the formula is given by the partial derivatives, and in every other coordinate system, I'll just define the primed coordinate components by the tensor transformation law. You could do that, and you would get a derivative that obeys the tensor transformation law, but its definition would depend on a particular coordinate system. And we don't want to do that for formulating the theory of general relativity, since the equivalence principle and all those other ideas motivate the idea that the theory should be formulated so that it holds in any coordinate system without having a preferred coordinate system involved in any way. So instead of a preferred coordinate system to get us a preferred derivative operator, we're going to use the fact that we have available a metric. The key ingredient for the covariant derivative is the metric g mu nu. Now, I'm going to list 6 conditions that our covariant derivative is going to satisfy. I can't derive these conditions. They're just very natural things that give you a natural derivative. And indeed, it is the derivative that Einstein used and that he used to construct his theory, which has been experimentally verified. So ultimately, it's experiment that tells you these conditions are the good ones to consider. But I hope you'll find them plausible. So the first condition is that any derivative operator should be linear. So if you act a derivative on some a times t plus b times s, where a and b are real numbers, and t and s are tensors, then it should be the case that the answer is a times the derivative of t plus b times the derivative of s. Every derivative operator we can think of ought to behave like that. And there also should be a Leibniz rule, which is now for tensor products of derivatives. If we have t tensor s and we take its derivative, that ought to be the same as the derivative of t tensor s plus t tensor the derivative of s. What else would a good derivative do? Well, we would very much like it to behave like the derivative we know and love, where that derivative works. And so in particular, on scalars, it should reduce to the partial derivative, because the partial derivative does obey the tensor transformation law when you're acting on a scalar. Now, there's another condition related to scalars that is a little less obvious, but it's a natural condition you can impose that makes things simpler. And again, it's the one that was imposed by Einstein and has been verified as the correct derivative to use in general relativity. And that's if you take a second derivative of a scalar, del mu del nu f, and you take the second derivative in the opposite order, it should commute. Now, this is not going to be true when our covariant derivative acts on tensors, but for scalars, it will be true. And this condition is called the torsion-free condition. You could relax it, and you could look to see if there's evidence for torsion in nature, and there isn't. And finally, or second to finally, there's a condition that really has to be there or the notation would totally break, which is the idea that the derivative must commute with contraction. So commute with contraction means if you had some tensor and you were taking its derivative first, contracting, it should be the same as taking the derivative and then contracting. So the fact that we can drop the parentheses here is this hidden property commute with contraction that we're going to make sure our derivative operator imposes. So the equation on the right here, the point is we've now written a rank 4 tensor and then contracted. And on the left here, we've contracted our rank 3 tensor to get a rank 1 tensor and then taken the derivative. And those have to be the same thing. And the very last condition we're going to impose is where the metric gets involved. Just down here at the end, we're going to impose that del mu g alpha beta equals 0. And this generalizes the property that in flat space-time, in inertial coordinates, we had del alpha, del mu, eta alpha beta equals 0, just as a statement that eta was minus 1, 1, 1, 1 on the diagonals, and so the derivatives vanished. That now gets promoted to this covariant derivative, better annihilate the metric in this way. Now the key point about these 6 conditions is that every one of them is tensorial. The thing we are defining, this triangle, is a map from a rank KL tensor to a rank KL plus 1 tensor. I should write that down. Right? It just adds one downstairs index, so it gives you a tensor back. You can see that all these conditions we've imposed are just good tensor equations. And so if we successfully get a derivative operator by imposing these conditions, we will absolutely be guaranteed that it satisfies the tensor transformation law as we set out to do. So let's go ahead and see what we can do with these conditions. Now, for the first two to be satisfied, a good starting point is the partial derivative, say, of a vector, because that's linear and obeys the Leibniz rule. But we don't want to restrict ourselves to that because we know that's not going to work with the other conditions. So we're just going to add a term that preserves linearity in the Leibniz rule. And the most general term that does that is just some linear map on the vector v, which can then be represented as a 3-index object, 1 index alpha to eat up the vector index, and then 2 more indices to be the free indices associated with nu, the vector index, and mu, the index we're taking the derivative with respect to. So to satisfy 1 and 2, we'll define our covariant derivative with this correction term here. And this correction term, once we've imposed all the conditions, are going to be called Christoffel symbols. And we say symbols rather than tensors because these won't obey the tensor transformation law. And for that reason, we don't worry about the up-down index placement. We just write them on top of each other. They're not the components of a tensor. Take care, however, that if you read some other books like Wald will say that the Christoffel symbols are tensors. And his idea is that it's a tensor whose definition depends on the coordinate system. So you pick a coordinate system that these partial derivatives refer to, and you declare that these symbols are actually tensors, and therefore in other coordinate systems, you could get their coordinate components by the tensor transformation law. But then the point is this equation down here would no longer hold in those other coordinate systems. But in this class, we're just going to take the point of view that the Christoffel symbols are just collections of numbers. They don't define a tensor. This gives us a derivative that acts on vectors. We'd also like to be able to take derivatives of 1 forms and higher rank tensors. And we could just do the same thing and introduce some different Christoffel symbols for each kind of tensor. But we've added these additional conditions to help us out so we don't have to do that. In particular, consider a one-form omega. How would we get a derivative of a one-form omega? Well, we could contract that one-form omega with some vector v, and we already have the law, our derivative for the vector v. So if we take the derivative of this whole thing, well, omega nu v nu is a scalar, and so that has to be the same as the partial derivative acting on omega nu v nu by condition 3. And I've kind of used condition 5 here as well because strictly speaking I've done the tensor product of omega nu, the tensor product of omega and v, and then contracted. So conditions 3 and 5 together will help us get the desired rule for derivatives of one-forms. And how will we do this? Well, we can also use the Leibniz rule. So the left-hand side can be written as del mu omega nu v nu plus omega nu del mu v nu. And similarly, the right-hand side can be written partial mu omega nu v nu plus omega nu partial mu v nu. And now we can use our formula for vectors on the left-hand side to expand this out. So the second term here will become omega nu times partial mu v nu plus our Christoffel symbol nu mu alpha v alpha. And then we still have the original term del mu omega nu times v nu, and that's equal to the right-hand side. So we see immediately that this term on the right-hand side is canceling with this term on the left-hand side. And then we have some terms proportional to v nu, and this term is proportional to v alpha. But let's just call that v nu so it looks like the other terms. So now I have to change the alpha to a nu in the Christoffel symbol. But since I already used a nu up here, I better change that to some other symbol like beta. And then this omega nu becomes omega beta. And now in this equation, I have 3 terms, all proportional to v nu. And so I can write those out as v nu. And then from the left-hand side, I have del mu omega nu. And then also from the left-hand side, I have plus omega beta, gamma beta mu nu. And then from the right-hand side, which I'll move over, I have minus del mu omega nu. And this is all equal to 0. We want to impose that this is true for any vector v, not just one specific one. And so we find that what's multiplying it here must vanish, and that gives us our desired formula for the derivative del mu omega nu of a one form. Moving things to the right-hand side, it's equal to the partial derivative del mu omega nu. And now we have a gamma term, but it comes with a minus sign, beta mu nu omega beta. And that is our formula for the derivative of a one form. Now, let's compare to the derivative of a vector. Up here we have the derivative of a vector. And now here we have the derivative of a one form. And the Christoffel symbols appear. And they look similar, but there's a crucial difference. There's a minus sign for the one form, and the indices are in slightly different places. This should have said beta, But the index placement is easy to understand because it's the only way it could be allowed by the notation. So if you have to remember this formula for the covariant derivative of a one form, first you write down the partial derivative, then you memorize that it's a minus sign, and then to figure out where the indices go here, well, it had to be a down index on the omega, and it has to be summed over because it's a linear map. And so you need an up index beta on the Christoffel symbol, and then the two down indices are just the ones that you took the derivative with respect to and the index on the one form itself. So these are the this is the law for a vector, this is the law for a one form, and then more generally, for an arbitrary tensor, the way it works is you just get one term for each kind of index. For example, if you wanted the derivative of a tensor t upper alpha beta lower gamma, what you would do is you would first write down the partial derivative term. That's always going to be there. And then you add terms to it, one for each index. So a plus for the upstairs index alpha, it's going to say gamma and then t. A plus for the upstairs index beta, it's going to say gamma and then t. And then a minus for the downstairs index gamma, which is also going to say gamma and then t. And now I just fill in the indices according to the way they would go in this law. So I always contract the index I'm working on with a corresponding index in the Christoffel symbol. So I'll call it lambda, and here I contract alpha because that's the one I'm working on. Then the upstairs alpha has to go in the upstairs slot of the Christoffel symbol. And what's left for the downstairs? Well, the mu. And then we just fill in the indices we're not working on here on the symbol t. Then we do the same thing for the next one. Now we're working on beta. So we leave alpha as is. We change beta to a lambda to sum over. And then gamma is left as is. Lambda goes downstairs to get summed over. Beta, the index we're working on, goes upstairs. And mu, the derivative index, stays downstairs. And for the last term, now we're working on lower gamma. So that changes to a dummy index lambda. Alpha and beta stay the same. Now the dummy index lambda has to be contracted with an upstairs index lambda. And mu is the one we're working on. And what's left for this? Well, it has to be the gamma that was turned into a dummy index. And so that's how you can get the rule for applying the covariant derivative for any rank tensor. The next condition we're going to use is condition 4, the torsion-free condition. It says that on any scalar f, if we do del mu del nu, that needs to be the same thing as doing it in the reverse order, del nu del mu. Now for expanding out these kinds of equations, it's usually easier to do the outer covariant derivative first and just think of the inner one as some tensor, in this case, a one form. So we need to use the one form rule for expanding out covariant derivatives. We have a partial derivative of that one form, del nu f, and then we correct with a minus sign with gamma with some dummy index lambda contracted with that one form. Now del lambda f, and then the mu nu come along for the ride downstairs. And then on the right-hand side, we just have the same thing with mu and nu interchanged. Now we can notice that our one form, del nu f, well, that's actually the same thing as partial nu f. That was one of our properties, property 3. The covariant better agree with the partial on scalars. And so what we have down here is just partial mu, partial nu f, and on the other side, similarly, partial nu, partial mu f. These are just ordinary partial derivatives, so by equality of mixed partials, these terms cancel. Now with the remainder, we can factor out the del lambda f and write it as del lambda f contracted with gamma lambda mu nu minus the same thing contracted with gamma lambda nu mu. And that then has to equal 0. And because this needs to hold for any function f, we conclude that the thing in parentheses actually has to vanish. And this gives us the consequence in terms of the Christoffel symbols of our torsion-free assumption. It's that the Christoffel symbols are actually symmetric on the lower two indices. So let's add that up here in a different color. Since it's a consequence of the torsion-free assumption, we don't think of it as the assumption. But we will always have this assumption, and so our Christoffel symbols will always be symmetric in the lower two indices. Now we've used every condition except for the last one, the metric. Let's see what that gets us. The last condition was metric compatibility. Del mu g alpha beta equals 0. Now g alpha beta is just some tensor. It's got two downstairs indices, so we can expand this out using the rule for covariant derivatives for downstairs indices. So we get one term where we're working on the alpha, so that flips to a lambda, and there's an upstairs lambda, and then we just have a mu alpha, and then another term where we're working on the beta. So similarly, we have a lambda, but now it's g alpha lambda, and we have a mu beta on the bottom. And what we'd really like to do is solve this equation for gamma to complete the construction of the Christoffel symbols. And the trick to doing that is to consider the equation in cyclic permutations. So if this is equation 1, then we can make another equation 2 by considering just del alpha g beta mu. So I've cyclically permuted the indices, and now I just have to do the same on every term. So this one becomes partial alpha g beta mu. And then over here, the lambdas stay the same. Beta swaps to mu, alpha swaps to beta, and mu swaps to alpha. And similarly on this last term, the lambdas are the same. Alpha goes to beta, beta goes to mu, mu goes to alpha. And we'll call that equation 2. And then finally, we're going to do it one more time. Consider the last cyclic permutation, del beta g mu alpha, which also equals 0 by assumption, and that becomes partial beta g mu alpha. And then I have to swap indices appropriately on this one as well. And finally on the last one, doing the same cyclic permutations. And now I just have 3 copies of the same equation, but labeling the indices different things. But this is progress, because now I can do the following. I can consider equation 1 minus equation 2 minus equation 3. So these are all equal to 0, so I'll have 0 equals. And what will I get on the right-hand side? Well, let's take a look at these terms. There's not much that I'm going to be able to do with the partials, so I'll just have partial mu g alpha beta minus partial alpha g beta mu minus partial beta g mu alpha. And the remaining terms, there's going to be some cancellations. So let's look at this one. Now we just showed by the torsion-free property that we can swap the indices on the lower part of the gamma. We can also swap the indices on the metric. It's a symmetric tensor. So if we look around, we'll find that another term, this one, is actually the same term. It's just written alpha mu beta lambda instead of mu alpha lambda beta. And because we're subtracting equation 1 minus equation 2, these are actually going to cancel from our new equation. Let's look at this term. If we look around, we should find one that looks the same. I see down here, we just have beta mu instead of mu beta, and lambda alpha instead of alpha lambda. Again, these are coming with the same sign in their respective equations, but we're subtracting 3 from 1, and so they're also going to cancel. Now the last terms, involving the Christoffel symbols are also identical, but they're appearing in equations 2 and 3, which are being added together with the same sign. They're both being multiplied by -1 and added, and so this is going to become plus 2 gamma lambda alpha beta g lambda mu. And we've made real progress now because we just have one Christoffel symbol left. It's multiplied by a metric, but we know the cure for that. We just multiply by the inverse metric, contracted appropriately, g mu nu. And so now the metrics come together to give us a Kronecker delta, nu lambda. That's the definition of the inverse metric. And that just sets nu equals lambda up here. So the whole term becomes 2 Christoffel nu alpha beta. And then we also have the remaining terms got multiplied by the inverse metric g mu nu. So let's write those out again. All of this is equal to 0. And now we have our formula. Christoffel nu alpha beta is equal to 1/2 times the inverse metric g upper mu nu times del alpha g beta mu plus del beta, and I'm going to write this as g alpha mu. I find it easier to remember that way, minus del mu g alpha beta. And that's our formula for the Christoffel symbol that will be used a lot to actually calculate these things. So when you want to actually take derivatives, as they appear in the theory of general relativity, you'll be using covariant derivatives, and so you'll have lots of formulas involving partial derivatives and corrections with these Christoffel terms here. And you're going to need to know the Christoffel symbols for whatever metric you're working in, and this is the formula you'll use. So you pick a coordinate system, and you just compute these Christoffel symbols. They don't transform like tensors. They're not tensors. They're things you use to help find useful expressions for the covariant derivative, which does transform like a tensor. So we express our laws of physics in terms of the covariant derivatives, and we work with them as long as possible. But when it comes time to do a calculation, we pick a coordinate system, we compute the Christoffel symbols, and we expand out the covariant derivatives in terms of partial derivatives and the Christoffel symbols to actually do definite calculations.